Tonight, we will look at something that seems straightforward, but turns out to be one of the most incredible ideas in science. We are talking about the light year. You have likely heard this term many times. Scientists say it all the time when they discuss outer space. Here is something most folks do not get though. Once you really grasp what a light year actually is, once you fully comprehend the distance it covers, your view of space changes completely. It is more than just a large number. The distance is so enormous that our minds struggle to wrap around it. If you like the content, consider liking and subscribing to the channel, because by the time we finish tonight, you will know precisely why scientists rely on this measurement and why other options simply will not do the job. Get ready, we begin. We will start with something you know well: distance. You grasp distance in your regular life. You understand how far you need to go to reach the store, your job, or the neighbouring town. These are distances you can connect with because you've made those trips. You have a feeling for what they represent in terms of duration, in terms of work required, in terms of what you'll observe during the journey. A kilometre equals roughly the distance you can walk in 10 to 12 minutes if you maintain a normal walking speed. These units of measurement function wonderfully for regular life. When someone mentions the store sits 5 kilometers away, you have a rough idea of your driving time. You can picture the trip in your head. Perhaps you'll drive through a couple of traffic signals. Perhaps you'll notice some recognizable landmarks. The distance feels solid and understandable. When someone says a town sits 200 kilometers away, you can organize your trip based on that. That equals roughly 2 hours behind the wheel. You'll probably want to gas up your tank, perhaps pack some snacks. Think about stopping halfway for a break. These distances fit human scale. They match our existence and our background. We developed the ability to comprehend distances we can cover by foot in one day, distances we can observe with our eyes, distances that mattered for staying alive and finding our way around. However, these measurements begin to feel clumsy when we discuss really huge distances. The distance separating New York from Los Angeles equals roughly 4,500 kilometers. That remains a workable number. It takes about 5 hours on a plane. Folks travel that route regularly. They journey across the nation. They watch the scenery shift from cities along the eastern coast to flatlands in the middle, to mountain ranges of rock, to dry lands in the southwest, and at last to the western ocean shore. The trip takes a while, but it's doable. It falls within what humans can accomplish. You can picture yourself making that journey. Earth's distance around the middle measures roughly 40,075 kilometers. That's a big figure, but it remains something we can handle in our minds. Early explorers sailed completely around the planet, so we understand it's achievable to cover that distance, even though it requires months. Ferdinand Magellan's voyage required 3 years to circle the globe, from 1519 to 1522. Today's commercial planes can fly around Earth in roughly 45 hours if you could arrange connecting flights going all the way around. Earth seems large when you're standing on it, but it's not beyond what we can understand. It's a limited thing you could theoretically explore from end to end. Now let's go bigger. Earth to the Moon measures roughly 384,000 kilometers. This is the point where normal measurements begin to seem insufficient. 384,000 kilometers. That's tough to picture in any real way. It's not comparable to crossing the country by car. It's not comparable to sailing around the planet. It's something entirely different. There's no road you can take, no markers you can pass, no places to rest during the trip. It's simply distance. Pure distance through empty void. How would you even start to cover that much ground? The Apollo space travelers required roughly 3 days to go from Earth to the Moon using strong rockets that sped them up to roughly 11 kilometers each second. That equals roughly 39,600 kilometers every hour, about 400 times quicker than driving on the highway. Consider that for a second. 400 times quicker than you've ever driven a vehicle. And even traveling at that amazing speed, which demanded some of the strongest rockets humans ever constructed, consuming huge quantities of fuel, it still required 3 days. 3 days moving through empty void at speeds no person had ever felt before, just to arrive at our closest neighbour in space. And that's only to the Moon, the nearest body in space to Earth. The Moon sits so near that you can observe it without any help. You can make out features on its surface using simple binoculars. It's right there hanging above. And still, reaching it takes 3 days in a rocket. When we begin discussing the distance to other worlds, to our sun, to other suns, kilometers turn completely worthless. The figures become so massive that they stop having meaning. They turn into abstract symbols written down instead of distances you can relate to in any manner. The distance from our planet to the Sun equals roughly 150 million kilometers. Try to see that in your mind. You're unable to, aren't you? Your mind simply registers it as a really large figure, but you lack any natural feeling for what it represents. Nothing in your regular day readies you for a distance that massive. Nothing in human development prepared us to consider distances this enormous. We developed to comprehend the distance to the next water location, the distance to where we hunt, the distance we could cover by foot in one day. We didn't develop to understand 150 million kilometers. The Apollo craft that carried space travelers to the Moon moved at roughly 11 kilometers each second on average. Traveling at that speed, reaching the Sun's distance would require roughly 160 days, over 5 months. The quickest spacecraft people have ever constructed, the Parker Solar Probe, moves at speeds reaching 192 kilometers each second when it's near the Sun, using the Sun's gravity to fling itself to greater and greater speeds. Even traveling at this amazing speed, which equals roughly 17 times quicker than the Apollo craft, the probe still requires months to finish its circles around the Sun, and the Sun sits close. It's right here in our space, neighborhood. It's the Sun we circle. It's where all the brightness and warmth that enables life on our planet comes from. We observe it daily. It's familiar. And still it sits 150 million kilometers distant. A distance so enormous that even our quickest spacecraft requires months to cross it. When we begin discussing distances to other suns, even our Sun's distance turns tiny by comparison. Our Sun is our nearest star, and it sits 150 million kilometers away. The following nearest star, Proxima Centauri, sits roughly 266,000 times more distant than that. 266,000 times more distant than a distance that already requires our quickest spacecraft months to traverse. This is the reason astronomers required a different measurement unit. Not because they enjoy making things complex, not because they wish to confuse folks with large figures, but because kilometers simply don't function when you're measuring space distances. Using kilometers to measure distances to stars would resemble using millimeters to measure the distance separating countries. Technically achievable, but totally impractical. The figures turn so massive they stop having all meaning. They quit being distances and turn into just figures. Abstract mathematical ideas that don't link to anything in our background, so scientists came up with something different, the light year. However, here's what you must grasp right from the beginning. A light year doesn't measure time. I understand it contains the word year in it, which makes it seem like time, but it's not. A light year measures distance. It equals the distance that light covers in 1 year. Now, why base a measurement on light? Because light is special. Light is the quickest thing in space. Nothing can move quicker than light. It's not simply a speed barrier that we haven't broken through yet. It's a basic law of how things work. The speed of light is a constant, unchanging, identical everywhere in space. Whether you're on our planet, on Mars, in a different galaxy, or at the boundary of what we can observe, light always moves at the identical speed. Light moves at roughly 300,000 kilometers each second. Let me repeat that because it matters. 300,000 kilometers each second. Every single second, light covers 300,000 kilometers. This isn't a rough guess or an estimate. It's been measured with amazing accuracy. The precise value equals 299,792.458 kilometers each second. But for what we're doing, 300,000 kilometers each second works fine. That's amazingly quick. To give you context, light can circle Earth's middle roughly 7.5 times in 1 second. In the duration it requires you to snap your fingers, light could go around the entire world multiple times. In 1 second, light could go from New York to Los Angeles and return roughly 37 times. It's a speed that's nearly impossible to picture because nothing in our regular experience moves anywhere close to that quick. The quickest thing most folks experience is an airplane. A commercial jet flies at roughly 900 kilometers hourly, or roughly 0.25 kilometers each second. Light moves over 1 million times quicker than that. The quickest car ever constructed, the Thrust SSC, reached roughly 1,200 kilometers hourly, or roughly 0.33 kilometers each second. Light equals roughly 900,000 times quicker. Even the quickest spacecraft we've constructed, the Parker Solar Probe, at 192 kilometers each second at its highest speed, still equals only roughly 0.064% light speed. It's traveling amazingly quick by human measures, but compared to light, it's crawling. When you flip a light switch, the light arrives at your eyes, basically instantly because the room is so tiny. The light moves from the bulb to your eye in roughly 10 billionths of a second. That's so quick that there's no noticeable pause. As far as your brain knows, the light shows up instantly, but the light did move. It required time. It's simply that the time was so brief, you couldn't possibly notice it. When you observe the sun above, you're actually observing it as it existed 8 minutes and 20 seconds earlier, because that's the duration light requires to move from the sun to our planet. The sun sits so distant that even light moving at 300,000 kilometers each second needs over 8 minutes to span the distance. This has an interesting consequence. If something occurred on the sun right now, if it suddenly shifted color or dimmed or even blew up, we wouldn't discover it for over 8 minutes. The event would occur, but the light carrying details about that event would still be moving toward us. We'd keep observing the sun as it existed, not as it is, for over 8 minutes. When you look at the moon, you're observing it as it existed roughly 1.3 seconds earlier. Not much of a pause, but still a pause. When space travelers walked on the moon and communicated with mission control on our planet, every word they voiced required 1.3 seconds to arrive at Earth, and every answer from mission control required 1.3 seconds to arrive at the moon. This produced a nearly 3-second gap in every exchange. You can hear this pause in the audio recordings. There's always this wait, this lag, because the radio waves carrying their voices moved at light speed. And even light requires time to span the distance between our planet and the moon. Light doesn't move instantly, it has a speed, and that speed, while amazingly quick, remains limited. This is among the most significant discoveries in the study of how things work. Before the late 1600s, most folks assumed a light moved. Instantly, you opened your eyes and you observed things immediately, so it appeared like light must be instantaneous. However, in 1676, a Danish astronomer named Ole Rømer made a careful observation of Jupiter's moons and noticed something odd. The times when the moons vanished behind Jupiter changed depending on where our planet was in its circle. When our planet was nearer to Jupiter, the eclipses occurred sooner than predicted. When our planet was more distant from Jupiter, they occurred later. Rømer understood this was because light required time to cover the different distances. He figured that light required roughly 22 minutes to span the width of Earth's circle. His calculation wasn't completely accurate because he didn't understand the precise size of Earth's circle. However, he demonstrated that light has a limited speed. Today we understand light's speed with amazing accuracy. We've measured it using lasers, atomic timekeepers, and advanced equipment. We've confirmed that it's constant, that it doesn't shift depending on how quick you're traveling or where you are. And we've discovered that this speed, this constant, is woven into the basic structure of the universe. It's not simply the speed that light happens to move at. It's a basic property of space-time itself. So a light year equals the distance light covers in 1 year at this speed. Let's figure that out. Light moves at 300,000 kilometers each second. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. If we multiply all of these together, 300,000 times 60 times 60 times 24 times 365, we get roughly 9.46 trillion kilometers. To be more accurate, it's 9,460,730,472,580.8 kilometers. However, for simplicity, we usually just say 9.46 trillion kilometers. That's what a light year equals. 9.46 trillion kilometers. Not a measure of time, but a measure of distance. The distance that light, the quickest thing in space, covers in 1 year. And that's the figure we're going to attempt to comprehend tonight. Because comprehending what a light year represents is crucial to comprehending our location in space, the distances separating stars, and the true size of everything that exists. However, first, we must discuss what a trillion actually represents. Because most folks have no natural feeling for how massive this figure really is. We use words like million, billion, and trillion in regular conversation. We hear about government spending in the trillions, about extremely wealthy people, about millions of folks, but we don't really comprehend the massive differences separating these figures. They all sound like big figures, so we handle them as roughly the same. However, they're not. The differences separating them are shocking. A million equals 1,000 thousands. If you saved $1 every day, beginning today, and continuing without ever stopping, you'd have $1 million in roughly 2,740 years. That's a long duration, but it's imaginable. You can picture a timeline going back 2,740 years. That brings you back to ancient Greece, to the early Roman Republic, to a time when people were already constructing cities, writing books, building civilizations. It's an understandable span of time. 1 billion equals 1,000 millions. Now we're jumping up by a factor of 1,000. If you saved $1 every second, not every day, but every single second, you'd require roughly 32 years to save $1 billion. That's more than the duration it requires for a generation to mature. If you began counting seconds when you were born and counted continuously without sleeping, eating, or taking any breaks whatsoever, you'd be 32 years old when you reached 1 billion. Consider that. 1 million seconds equals roughly 11.5 days. That's imaginable. You can picture a period of 11.5 days. It's under 2 weeks. However, 1 billion seconds, that's 32 years. The jump from 1 million to 1 billion is huge. 1 trillion equals 1,000 billions. And here's where figures begin to totally lose their link to anything we can relate to. If you counted to 1 trillion, counting one figure each second without stopping, it would require you roughly 31,700 years. Let me give that context. That's longer than all of written human history. Farming, the basis of civilization, was only invented roughly 10,000 years earlier. Before that, all people lived as hunter-gatherers, traveling from location to location, following animal groups and seasonal plants. Writing systems showed up roughly 5,000 years earlier in Mesopotamia. The pyramids of Egypt were constructed roughly 4,600 years earlier. The wheel was probably invented roughly 5,500 years earlier. To count to 1 trillion, you'd need to have begun counting before any of that occurred. You'd need to have begun when people still lived in small tribal groups. When there were no cities, no nations, no written language, no farming, no permanent settlements. You'd need to have been counting through the entire span of human civilization, through every invention, every discovery, every empire that rose and fell, through every war, every peace, every triumph and tragedy in human history, and you'd still be counting today, and you'd still have thousands of years remaining before you reached 1 trillion. Let me attempt to make this even more solid. 31,700 years earlier, modern people were living in the final ice age. We were using stone tools. We were hunting woolly mammoths and giant ground sloths. We had barely started to spread across the globe. Modern people had only recently left Africa and were just beginning to populate Europe and Asia. There was no language as we understand it today. No art beyond the most basic cave paintings. No technology beyond sharp rocks and wooden spears. That's how far back 1 trillion seconds brings you. And a light year equals 9.46 trillion kilometers. Every single one of those kilometers is a kilometer. It's not an abstract unit, it's a real distance. The distance you could walk in roughly 10 to 12 minutes at a normal pace. And there are 9.46 trillion of those individual kilometers in one light year. 9.46 trillion separate, distinct kilometer-long segments, each one the length of a walk to your local store. So when we say a light year equals 9.46 trillion kilometers, we're discussing a distance that overshadows anything in our regular experience. You can write it down. You can calculate with it. You can use it in math problems. However, grasping it naturally is nearly impossible. Our minds simply didn't develop to handle figures this massive. We developed to count the number of folks in our tribe, the number of animals in a group, the number of days until the seasons shift. We can count to a few hundred, perhaps a few thousand if we really focus. However, 9.46 trillion, that's so far beyond what our minds can handle that it might as well be infinity. The best way to comprehend a light year is to construct up to it slowly, beginning with distances we can understand and scaling up step by step. We're going to take this trip slowly, travelling from the familiar to the unfamiliar, watching as distances that appear vast turn tiny compared to what comes after. Let's begin with 1 light second, 300,000 kilometers. That's roughly the distance from our planet to the moon and 3/4 of the way returning. Consider what that represents. Light leaves our planet, moves all the way to the moon, which sits 384,000 kilometers away, bounces back and gets roughly 3/4 of the way to Earth. And all of that occurs in 1 second, 1 single second. When space travelers on the Moon communicated with Mission Control in Houston during the Apollo missions, there was a communication pause of roughly 1.3 seconds each direction. The space travelers would say something and Mission Control wouldn't hear it for 1.3 seconds because the radio wave moving at light speed needed that long to make the trip. When Mission Control answered, their answer required another 1.3 seconds to arrive at the Moon. So every exchange had a nearly 3-second pause built in. It's subtle when you listen to the audio files, but it's always there. There's this wait, this lag, because of the distance the waves had to cover and because nothing, not even radio waves, can move quicker than light. 1 light minute equals 60 light seconds, 18 million kilometers. Our Sun sits roughly 8 light minutes away from our planet, which equals roughly 150 million kilometers. So, 1 light minute is roughly 12% of the distance from our planet to the Sun. If you could somehow stand on the Sun, which you obviously can't because it's a ball of plasma, with a surface temperature of roughly 5,500 degrees Celsius. But if you could somehow stand there and look at our planet, you'd be observing Earth as it existed 8 minutes and 20 seconds earlier. If our planet suddenly blew up, you wouldn't discover it for over 8 minutes. The event would occur, but the light from that event carrying the details about it would require over 8 minutes to span the distance between our planet and the Sun. This has practical consequences for space exploration that most folks don't consider. When NASA operates rovers on Mars, there's always a communication pause because Mars sits so distant. At its nearest, when our planet and Mars are on the identical side of the Sun in their circles, Mars sits roughly 32 million kilometers from our planet, which equals roughly 2 light minutes. At its most distant, when our planet and Mars are on opposite sides of the Sun, the distance equals roughly 400 million kilometers, roughly 22 light minutes. This means when the Perseverance rover is operating on Mars, every command sent from our planet requires between 2 and 22 minutes to arrive, depending on where Mars is in its circle. And any information the rover sends back requires the same amount of time to arrive at Earth. You can't drive a rover on Mars in real time like you'd drive a remote-controlled car on our planet. The pause is too long. Instead, NASA engineers must plan the rover's activities carefully. They examine images from previous days, plan a route, write a sequence of commands, send those commands to Mars, and then wait. If something goes wrong, if the rover gets stuck on a rock or encounters an obstacle, they can't react instantly. They must wait for the details to arrive at Earth, which requires anywhere from 2 to 22 minutes. Then they must examine what went wrong, figure out a solution, write new commands, send those commands, and wait another 2 to 22 minutes for them to arrive. A problem that might require seconds to solve with a remote-controlled car on our planet can require an hour or more to solve on Mars. 1 light hour equals 60 light minutes. That's roughly 1,080,000,000 kilometers, over 1 billion kilometers. That's a distance so enormous that even picturing it is difficult. The planet Saturn at its nearest approach to our planet sits roughly 1.2 light hours away. Saturn is among the most distant planets you can observe without help from our planet. A beautiful ringed world that's been observed since ancient times, and it sits roughly 1.2 light hours away. When the Cassini spacecraft was circling Saturn from 2004 to 2017, taking amazing close-up photographs of the planet and its moons, there was over an hour of pause between when it took a picture and when that picture arrived at Earth. The spacecraft would take a photo, convert it to digital information, transmit it as a radio wave moving at light speed, and over an hour later, scientists on our planet would receive it. This meant that Cassini couldn't be controlled in real time. Engineers and scientists couldn't watch what the spacecraft was observing and adjust its path on the fly like you might steer a car or pilot a drone. Instead, they had to program entire sequences of commands days or weeks ahead of time, upload them to the spacecraft, and trust that Cassini would carry them out correctly. If something went wrong, the spacecraft had to be smart enough to handle it on its own, to recognize the problem and switch to a safe mode. Because by the time the problem was reported back to our planet and new commands were sent, over 2 hours would have passed. The situation could have shifted completely in that time. 1 light day equals 24 light hours, roughly 25,900,000,000 kilometers. We're now discussing distances where even our quickest spacecraft turn amazingly slow by comparison. Voyager 1, the spacecraft that launched in 1977 and is currently the most distant human-made object from our planet, sits roughly 24 light hours away as of 2025. It's been moving for nearly 50 years, travelling at roughly 17 kilometers each second, which equals roughly 61,200 kilometers hourly. That's amazingly quick by any human measure. At that speed, you could go from one side of the United States to the other in roughly 2 minutes. And still, after nearly 5 decades of constant travel through the vacuum of space with nothing to slow it down, Voyager still hasn't covered 1 full light day from our planet. This is roughly the distance to the heliopause, the boundary where our sun's influence ends and interstellar space starts. The heliopause is where the solar wind, the constant stream of charged particles flowing out from the sun in all directions, finally slows down and mixes with the interstellar medium, the thin gas that fills the space separating stars. Voyager 1 crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. It was a historic moment, a milestone in human exploration. However, it's still within 1 light day of the sun. It's still in cosmic terms right here in our neighborhood. 1 light week equals 7 light days, roughly 181 billion kilometers. Now we're in a region where nothing human-made has ever been, and nothing will be for decades or centuries to come. This is deep space, far beyond the planets, far beyond anything we've directly explored. Out here, the sun would no longer show up as the overwhelming source of light and heat it is from our planet. It would show up as just a bright star, brighter than other stars certainly, but just a point of light in the darkness. If you were somehow out here floating in space at 1 light week from the sun, you'd observe the sun as a brilliant star. However, you'd also observe thousands of other stars scattered across the black sky. You'd understand perhaps for the first time that the sun is just one star among many. 1 light month is roughly 30 light days, roughly 778 billion kilometers. At this distance, if you looked back at the sun through a telescope, you'd observe it as just another star, not much brighter than many others in the sky. The solar system with all its planets and moons and asteroids and comets would be barely visible. Even with a powerful telescope, you might observe Jupiter as a faint dot, but the inner planets would be lost in the sun's glare. Everything we consider as the solar system, all the planets we've studied and sent spacecraft to, all the worlds we understand would be compressed into a tiny region around an ordinary star. And 1 light year equals 365 light days. It's 12 light months. It's 52 light weeks. It's 8,760 light hours. It's 525,600 light minutes. It's 31,536,000 light seconds. See how rapidly the figures scale up? We began with 1 light second, which was already an enormous distance by human measures, roughly the distance from our planet to the moon and most of the way back. And we've been multiplying by larger and larger figures: 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 7 days in a week, 30 days in a month, 12 months in a year. And we're just now arriving at 1 light year, 9.46 trillion kilometers. That's the distance light covers in 1 year, traveling at 300,000 kilometers every single second for 365 days straight. And this is the basic unit scientists use to measure the distances separating stars, because stars are separated by distances measured in light years. And nothing smaller makes sense when you're dealing with these vast space scales. So why do scientists use light years? Because every other choice is worse. Picture if scientists used kilometers for everything. Proxima Centauri sits roughly 40 trillion, 140 billion kilometers away. That's awkward, hard to remember, and doesn't give you any natural sense of the distance. However, if I tell you Proxima Centauri sits 4.24 light years away, that's cleaner. You can compare it to other distances. If one star sits 4 light years away and another sits 40 light years away, you immediately understand the second is 10 times more distant. Light years also link distance and time usefully. When you look at a star 4 light years away, you're observing light that left 4 years earlier. You're looking into the past. This link becomes crucial when studying space. Light's speed is not just quick, it's the speed barrier of space. Nothing can go quicker, and this isn't a technological limitation that we might overcome with better engineering or more powerful rockets. It's a basic law of how things work, built into the very structure of space-time itself. Light's speed isn't just a speed. It's a space constant that defines the relationship between space, time, energy, and matter. Einstein's theory of special relativity, published in 1905, showed that as objects approach light speed, odd things occur. These aren't just theoretical predictions, they're observed facts confirmed by countless experiments over the past century. Time slows down for the moving object relative to stationary observers. This is called time dilation, and it's been measured directly. The object's mass effectively increases, or more accurately, its resistance to acceleration increases. It turns harder and harder to speed up. The amount of energy needed to speed it up increases without limit as you approach light speed. To actually reach light speed would demand infinite energy, which is impossible. Space doesn't contain infinite energy. Therefore, nothing with mass can reach light speed. Let me explain why this occurs. In our regular experience, if you're on a train traveling at 50 kilometers hourly and you throw a ball forward at 20 kilometers hourly relative to the train, someone standing on the ground would observe the ball traveling at 70 kilometers hourly. The speeds add. This seems obvious, and it functions perfectly well for regular speeds. However, Einstein showed that this simple addition doesn't function when you're dealing with speeds near light speed. If you're on a spacecraft traveling at half light speed and you shine a flashlight forward, you might think the light would travel at 1.5 times light speed, at least from the viewpoint of someone watching you. However, it doesn't. The light still travels at precisely light speed, 300,000 kilometers each second, both from your viewpoint on the spacecraft and from the viewpoint of someone watching you from outside. This seems impossible. How can the light be traveling at the identical speed for both observers when one observer is already traveling at half light speed? The answer is that space and time adjusts to keep light speed constant. If you're traveling very quick, time literally runs slower for you from the viewpoint of a stationary observer. And distances in the direction you're traveling actually contract. These aren't optical tricks or measurement errors. They're real physical effects. Time and space are not absolute. They're relative depending on your motion. The only thing that's absolute, that's identical for everyone, regardless of how they're traveling, is light speed. This has been tested experimentally countless times. Particles in particle accelerators travel at speeds very near light speed. We can measure how long they live before decaying, and we find that particles traveling at 99.9% light speed live much longer than identical particles at rest. Time is literally traveling slower for them. This isn't theory, it's measured fact. GPS satellites circling our planet travel quick enough and are distant enough from Earth's gravitational field that time dilation turns measurable. The atomic timekeepers on GPS satellites run at a slightly different rate than identical timekeepers on the ground. If GPS didn't account for this time dilation effect, your GPS navigation would be off by several kilometers within just a few hours. The fact that GPS functions is proof that time dilation is real. Cosmic rays, high-energy particles from space, create muons when they hit the upper atmosphere. Muons are subatomic particles that decay very rapidly with a half-life of roughly 2 microseconds. At this rate, even traveling near light speed, muons, created in the upper atmosphere, shouldn't be able to arrive at the ground before decaying, and still, we detect muons at ground level all the time. Why? Because from our viewpoint, the muons are traveling so quick that time dilation extends their lifetime. What's 2 microseconds from the muon's viewpoint turns much longer from our viewpoint, long enough for them to arrive at the ground. Only massless particles like photons, which are particles of light, can move at light speed. Photons have no rest mass, so they don't require infinite energy to reach light speed. In fact, photons must always move at light speed. They can't slow down or speed up. From the moment they're created to the moment they're absorbed, they move at precisely light speed. No quicker, no slower. This is simply what photons do. It's their nature. This has deep consequences for space travel that go beyond just engineering challenges. Even if we developed perfect propulsion systems with access to unlimited energy, even if we solved every engineering problem imaginable, we still couldn't move quicker than light. The 4.24 light-years to Proxima Centauri represents a minimum travel time of 4.24 years, even in the most optimistic scenario where we could somehow speed up a spacecraft to nearly light speed. And that's just getting to the nearest star. Most destinations in space are much, much more distant. Some science fiction proposes ways around this limitation. Warp drives that bend space around a spacecraft, allowing it to effectively move quicker than light without actually traveling quicker than light through space. Wormholes that create shortcuts through space-time linking distant points in space. Hyperspace, an alternate dimension where the laws of how things work are different and quicker than light travel is achievable. These are creative ideas, and some, like warp drives, have a basis in theoretical physics. The Alcubierre drive, proposed in 1994, is a theoretical solution to Einstein's field equations that would allow quicker than light travel by contracting space in front of a spacecraft and expanding it behind. However, there are problems. The Alcubierre drive would demand exotic matter with negative energy density to function. No such matter is known to exist. Some physicists think it might be impossible on basic grounds. Even if exotic matter exists, you'd require an enormous amount of it, possibly more mass energy than exists in the entire observable universe. And there are causality problems. If you could move quicker than light, you could potentially move backward in time, creating paradoxes. Wormholes, if they exist, would likely be amazingly unstable and would collapse before anything could pass through them. Keeping a wormhole open long enough to move through it might demand more energy than exists in the entire universe. And again, there are causality problems. If wormholes allow quicker than light travel, they also allow time travel to the past with all the associated paradoxes. Hyperspace is pure speculation with no basis in known physics. It's a science fiction idea that makes for good stories but doesn't have any link to real physics or mathematics. There's no evidence that any such thing exists or could exist. As far as we understand, based on over a century of careful experiments and observations, light speed is an absolute barrier. It's not a challenge to be overcome with better technology. It's a basic law of nature. When we discuss stars that are hundreds or thousands of light years away, we're discussing distances that might be basically unreachable with any technology that's consistent with the laws of how things work as we comprehend them. The light year doesn't just measure distance. It measures a barrier, a limit, a boundary beyond which the normal rules of cause and effect begin to break down. Let's discuss Proxima Centauri because it's our nearest stellar neighbour and helps us comprehend these distances practically. Comprehending Proxima Centauri, the nearest star beyond our Sun, gives us a sense of what it means when we say, even the nearest stars are impossibly distant. Proxima Centauri is a small red dwarf star in the Alpha Centauri system, which is actually a triple star system. Two of them, Alpha Centauri A and B, are sun-like stars circling each other. They're similar in size and brightness to our Sun, and they circle their common centre of mass every 79.9 years in a slow gravitational dance that's been continuing for billions of years. If you could observe them up close, Alpha Centauri A and B would look like two suns circling each other against the darkness of space. Proxima Centauri is much smaller, roughly 1/8 the Sun's mass and 1/7 its width. It's so small and dim that you can't observe it without help. Even though it's our nearest stellar neighbour, you need a telescope to spot it. Red dwarfs like Proxima Centauri are the most common type of star in the galaxy, making up roughly 70% of all stars. However, they're all so dim that none of them are visible without help, despite being relatively common. When you look up at the night sky, every star you can observe without help is either larger and brighter than the Sun, or it's not a star at all, but a planet. Proxima Centauri sits 4.24 light-years away, roughly 40,140,000,000,000 kilometers. That's 40 with 12 zeros after it. To give this context, if you could somehow move at the speed of the quickest spacecraft people have ever constructed, the Parker Solar Probe, at 192 kilometers each second, it would require you roughly 6,800 years to arrive at Proxima Centauri. That's longer than all of written human history. Writing was invented roughly 5,000 years earlier. You could have begun your trip when people first learned to write, moved continuously at the quickest speed any human spacecraft has ever achieved, and you'd still be moving today, still thousands of years away from your destination. There have been proposals for quicker spacecraft. The Breakthrough Starshot initiative, announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner, proposes using powerful ground-based lasers to speed up tiny spacecraft to roughly 20% of light speed. The concept is elegant and scientifically sound, at least in principle. You construct a spacecraft that's essentially a computer chip with a camera weighing maybe a gram attached to an ultra-thin light sail made of reflective material, perhaps only a few atoms thick. Then you point massive arrays of lasers at it from our planet. The laser light pushes on the sail, and because the spacecraft is so amazingly light, it can be sped up to tremendous speeds. At 20% of light speed, which equals roughly 60,000 kilometers each second, a probe could arrive at Proxima Centauri in roughly 20 years. Add another 4 years for signals to move back to our planet at light speed, and you could potentially get information from Proxima Centauri in 24 years from launch. That's within a human lifetime, which is exciting. You could launch a mission when you're young and potentially observe the results before you die. However, the engineering challenges are enormous, perhaps impossible to overcome with current or near-future technology. First, you require amazingly powerful lasers. The proposal calls for a laser array with a total power of roughly 100 gigawatts. That's roughly the output of 100 nuclear power plants, all focused into a laser beam a few kilometers wide. This beam would need to track the tiny spacecraft as it speeds up, keeping the light precisely focused on the sail. Any deviation and the sail would drift out of the beam, and the acceleration would stop, leaving the spacecraft coasting at whatever speed it had reached. Second, the spacecraft needs to survive the trip. At 20% of light speed, you're traveling at 60,000 kilometers each second. At this speed, collisions with even tiny particles turn catastrophic. A speck of dust, something smaller than a grain of sand, hitting the spacecraft at this speed would release energy equivalent to a large bomb. The spacecraft would require shielding to protect it. However, any shielding adds weight, and weight is the enemy when you're attempting to speed up something with light pressure. The more the spacecraft weighs, the more power you require to speed it up, and the equation gets worse and worse as you add weight. Third, you require the ability to communicate with the spacecraft over 4 light-years of distance. The tiny probe would require a laser or radio transmitter powerful enough to send information back to our planet from 4 light-years away. At that distance, any signal spreads out enormously. The power needed to send a detectable signal is substantial, and you must fit this capability into a spacecraft the size of a computer chip. It's like attempting to shout across an ocean and be heard clearly on the other side. Fourth, you require to actually hit Proxima Centauri's star system and fly past it at the correct distance and angle to get useful information. At 20% of light speed, the spacecraft is moving so quick that it crosses the orbit of Mars in roughly 40 minutes. The entire width of our solar system from the Sun to Neptune is crossed in roughly 6 hours. You get one shot. There's no slowing down, no course corrections once you're up to speed, because slowing down would demand just as much energy as speeding up. And you don't have that energy available in a spacecraft weighing a gram. The spacecraft flies past Proxima Centauri at 60,000 kilometers each second, has maybe a few hours or at most a few days when it's near enough to take useful pictures and measurements, and then continues on into the void, never to be observed again, drifting through interstellar space forever. So, while Breakthrough Starshot is an interesting concept and it's based on real physics rather than science fiction, it remains highly theoretical. The technology doesn't exist yet, and there are formidable challenges that might be impossible to overcome. Even if we somehow constructed such a craft and successfully sent it tomorrow, it would be at least 20 years before it arrived at Proxima Centauri and another 4 years before we got any information back. That's a 24-year round trip for information, assuming everything functions perfectly, which in the history of space exploration has never been a safe assumption. And this is just to arrive at our nearest stellar neighbour, the nearest star to our Sun. With technology, we can actually construct today the kind of spacecraft we understand how to engineer and launch with current rockets and current materials and current computer systems. Getting to Proxima Centauri would require not decades, but millennia. We'd require to construct multi-generational spacecraft, massive vessels that could support human crews for thousands of years. The folks who arrived at Proxima Centauri would be the distant descendants of those who launched, perhaps hundreds of generations removed, living in a world they'd never left, moving to a destination they'd only heard about in stories passed down through the centuries. When you look up at the night sky, you're observing stars at various distances, and you're observing them as they were years or even centuries earlier. This is among the most deep consequences of the light year. Distance and time turn inseparable. You cannot separate where something is from when you're observing it. Light moves at a limited speed. It's amazingly quick, but it's not instantaneous. When light leaves a star and moves through space toward our planet, that trip requires time. And during that time, things can shift. The star might shift brightness, it might shift color, it might blow up. By the time the light arrives at your eyes, the star you're observing might be completely different from how it is right now, or it might not even exist anymore. Sirius, the brightest star in the night sky, sits 8.6 light-years away. When you look at Sirius tonight, you're observing light that left that star 8.6 years earlier. You're observing Sirius as it was when you were 8.6 years younger. If you're 20 years old, you're observing Sirius as it was when you were roughly 11, probably in middle school. If you're 40, you're observing it as it was when you were in your early 30s. The Sirius you observe tonight is Sirius from the past, not Sirius as it exists right now in this present moment. Now, Sirius is a stable main sequence star. It's not going to shift much over a few years or even a few decades. In 8.6 years, Sirius doesn't age noticeably. Stars shift very slowly from a human viewpoint over millions or billions of years rather than years or decades. However, the principle is what matters here. You're not observing Sirius as it is. You're observing Sirius as it was. You're looking back in time every time you look at a star. Vega is another bright star, roughly 25 light-years away. If you're 25 years old and you look at Vega tonight, you're observing light that left that star the year you were born. When that light began its trip toward our planet, you hadn't been born yet. You didn't exist. Your parents might have been looking up at that same star, observing light that left Vega 25 years before that, 50 years ago total. The Vega you observe tonight is a younger Vega, showing you what that star looked like a quarter century earlier, not as it is right now. Betelgeuse, the red supergiant in the constellation Orion, sits roughly 550 light-years away. It's among the most famous stars in the night sky, easily visible as the bright reddish star marking Orion's shoulder. The light you observe from Betelgeuse tonight started its trip toward our planet in the year 1474 during the Italian Renaissance, before Columbus sailed to the Americas, when Leonardo da Vinci was 22 years old and Michelangelo was about to be born. In 1474, the Byzantine Empire had fallen to the Ottoman Turks 21 years earlier. The printing press had been invented only roughly 20 years before. Most of Europe was still emerging from the Middle Ages. The modern world as we understand it didn't exist yet. And the light from Betelgeuse that you observe tonight started its trip back then. It's been moving through space for over 500 years, crossing the vast darkness between Betelgeuse and our planet to arrive at your eye tonight. Betelgeuse is a particularly interesting example because it's a massive star nearing the end of its life. Stars like Betelgeuse don't last as long as smaller stars like the Sun. They burn their fuel much quicker. At some point in the relatively near future, astronomically speaking, within the next 100,000 years or so, Betelgeuse will blow up as a supernova. When it does, it will briefly shine as bright as the full moon in our sky, visible even during the day. It will be a spectacular event, among the most dramatic astronomical events visible from our planet in human history. However, here's the thing. Betelgeuse might have already blown up. The explosion might have occurred centuries earlier. Maybe it occurred in the year 1600 or 1700 or 1800. However, we wouldn't discover yet. We wouldn't have any way of discovering. The light from that explosion would still be moving toward us through space, traveling at light speed, requiring 550 years to make the trip. So if Betelgeuse blew up in the year 1700, we won't observe it until roughly the year 2250. The star could already be gone right now, destroyed in a catastrophic supernova explosion, and we'd still observe it shining peacefully in the sky for centuries to come, completely unaware that we're observing a ghost, an image of something that no longer exists. Polaris, the North Star, sits roughly 445 light-years away. When its current light began moving toward us, the first permanent English colonies in North America hadn't been established yet. Jamestown wouldn't be founded for another 12 years. The Pilgrims wouldn't arrive at Plymouth Rock for another 26 years. William Shakespeare had just begun writing his plays. He'd written some of his early works, but hadn't yet written Hamlet, Macbeth, King Lear, or most of his other famous plays. The United States wouldn't exist for another 180 years. When that light from Polaris began its trip, the world was basically different from today. And tonight, that ancient light enters your eye. You're linked across space and time by photons that have been moving for 4.5 centuries. Within roughly 20 light years of our planet, there are roughly 130 known star systems. Some are single stars like our Sun. Others are binary systems with 2 stars circling each other, or even triple star systems like Alpha Centauri. Comprehending this stellar neighborhood helps us appreciate both the distances involved and the variety of stars that exist in our space backyard. Barnard's star is the second nearest star system to our planet after Alpha Centauri, roughly 6 light-years away. It's a red dwarf, much smaller and dimmer than the Sun. What makes Barnard's star particularly interesting is that it's travelling toward us relatively rapidly by stellar measures. It has the largest proper motion of any known star, meaning it travels across the sky quicker than any other star as observed from our planet. Over the course of decades and centuries, we can actually observe Barnard's star shift position relative to other stars. In roughly 10,000 years, it will be nearer to our planet than Proxima Centauri is now, becoming our new nearest stellar neighbour. However, even at its nearest approach, it will still be nearly 4 light-years away. The distances separating stars are so enormous that even when stars are travelling toward each other, it requires thousands or tens of thousands of years for that motion to make a noticeable difference in the distance between them. Wolf 359, roughly 7.9 light-years away, is among the quickest moving stars relative to the Sun, moving at roughly 119 kilometers each second. That's quick by stellar measures. Most stars in our region of the galaxy travel at speeds of a few tens of kilometers each second relative to each other. Wolf 359 is traveling much quicker. Still, even at this speed, it's traveling at only roughly 0.04% of light speed. Stars travel, but they travel slowly compared to the vast distances separating them. Even the quickest moving nearby star would require tens of thousands of years to cover a light year. Sirius, 8.6 light-years away, is actually a binary system with 2 stars circling each other. Sirius A is a bright white main sequence star, roughly twice the mass of the Sun. It's the brightest star in our night sky, partly because it's relatively near and partly because it's inherently quite luminous. Sirius B is completely different. It's a white dwarf, the dense remnant of a star that exhausted its nuclear fuel and collapsed. White dwarfs are fascinating objects. They're roughly the size of our planet, but have the mass of a star. Sirius B has roughly the mass of our Sun, compressed into a sphere roughly the size of our planet. This makes it amazingly dense. A teaspoon of material from Sirius B would weigh roughly 5 tons on our planet. The two stars circle each other every 50 years, locked together by gravity, each following an elliptical path around their common center of mass. The Milky Way is a spiral galaxy containing between 100 billion and 400 billion stars. That's a huge range because it's actually quite difficult to count stars in our own galaxy. We're inside it, like attempting to count trees while standing in the middle of a forest. Dust blocks our view in many directions. Dim stars are hard to detect, and the galaxy is so large that we can't observe all of it at once from our position. However, the best estimates suggest somewhere between 100 billion and 400 billion stars, with the most likely figure being around 200 to 300 billion. Our Sun is just one of these stars, an ordinary yellow dwarf star of average size and brightness. There's nothing special about our Sun from a galactic viewpoint. It's not the biggest, not the brightest, not the hottest, not the coolest. It's just a typical star, one among hundreds of billions, and it's located in one of the spiral arms roughly 26,000 light-years from the galactic center. 26,000 light-years. The light we observed from the center of our galaxy, if we could observe through all the dust blocking the view, left the galactic center 26,000 years earlier. When that light began its trip, people were still living as hunter-gatherers in the Stone Age. Farming hadn't been invented yet. There were no permanent settlements, no cities, no civilization as we comprehend it. Folks lived in small nomadic bands, following animal groups, gathering wild plants, using simple stone tools. Writing wouldn't be invented for another 21,000 years. Everything we consider as human civilization, everything from the first farms to the first cities, to the first writing, to all the ancient empires, to the modern world, all of it has occurred while light from the galactic center was moving toward us. And that light which left when people were still primitive hunter-gatherers arrives at our planet tonight. The Milky Way is roughly 100,000 light-years across from one edge of the spiral arms to the other. If you could somehow move at light speed, which you can't, it would require you 100,000 years to cross the galaxy from one side to the other. 100,000 years. Modern people, Homo sapiens, are roughly 300,000 years old as a species, so you could have begun crossing the galaxy when the first modern people appeared in Africa, moved at light speed for 100,000 years, and you'd only be 1/3 of the way across the galaxy today. The Sun circles the galactic center at a speed of roughly 230 kilometers each second. That sounds quick, and it is quick. At that speed, you could move across the United States in roughly 3 minutes. You could circle our planet in just under 3 minutes. However, even at this amazing speed, it requires the Sun roughly 225 million to 250 million years to complete one circle around the galaxy. The final time the Sun was in its current position in the galaxy, dinosaurs were just beginning to develop on our planet. The first dinosaurs appeared roughly 230 million years earlier. Since then, the dinosaurs developed, ruled our planet for over 160 million years, went extinct 66 million years earlier. Mammals took over, and people eventually developed, and the Sun has only just now returned to approximately the identical position in the galaxy where it was when dinosaurs first appeared. Among the most exciting developments in astronomy over the past few decades has been the discovery of exoplanets, planets circling stars other than our Sun. Until 1992, we understood of only one planetary system, our own solar system, with its 8 planets circling the Sun. We suspected other stars might have planets, but we had no direct evidence. Then in 1992, astronomers detected the first planet circling another star, a pulsar. In 1995, they found the first exoplanet circling a normal Sun-like star. And since then, the discoveries have exploded. As of 2024, we've confirmed the existence of over 5,000 exoplanets, with thousands more candidates waiting to be verified. The TRAPPIST-1 system, roughly 40 light-years away, contains 7 Earth-sized planets circling a small red dwarf star. 3 of these planets are in the habitable zone, where temperatures could potentially allow liquid water to exist on the surface. This discovery, announced in 2017, was revolutionary for several reasons. It showed that small red dwarf stars can host multiple rocky planets. Since red dwarfs are the most common type of star in the galaxy, making up roughly 70% of all stars, this suggests rocky planets might be extremely common throughout space. The TRAPPIST-1 system is also remarkable because the planets are packed tightly together. All 7 planets circle closer to their star than Mercury circles our Sun. However, because the star is so small and cool, 3 of the planets receive roughly the identical amount of energy from their star as our planet receives from the Sun. If you stood on one of these planets, you'd observe the other planets in the sky. Some appearing larger than our Moon appears from our planet. The planets are so near together that travel between them would be far easier than travel between planets in our solar system. When we observe the TRAPPIST-1 system today, we're observing it as it was 40 years earlier in 1985. If there's intelligent life on one of those planets, and if that life developed radio technology and started broadcasting signals into space, those signals would require 40 years to arrive at us. We'd be receiving signals today that were broadcast in 1985. And if we detected such a signal today and sent a response, it would require another 40 years for our response to arrive at them. They'd receive our reply in 2065. That's an 80-year round trip for a single exchange of details. You could ask a question and die of old age before receiving an answer. Let's consider what communication means when distances are measured in light years. This is among the most challenging and sobering aspects of the scale of space, and it has deep consequences for any future where humanity might attempt to establish settlements on other worlds or make contact with alien civilizations. Radio waves move at a light speed. They're electromagnetic radiation just like visible light, but with longer wavelengths. When we send radio signals into space, they spread outward in all directions at 300,000 kilometers each second. However, even at this amazing speed, the quickest speed achievable in space, communication across light years requires years. Voyager 1, our most distant spacecraft, is now roughly 24 light hours away from our planet. That means there's a communication pause of roughly 24 hours each direction. When mission controllers on our planet send a command to Voyager, that command requires roughly 24 hours to arrive at the spacecraft. The radio wave moves at light speed, covering roughly 25 billion kilometers to arrive at Voyager. Any information Voyager sends back requires another 24 hours to arrive at Earth. There's roughly a 48-hour pause for any two-way communication. If something goes wrong with the spacecraft, if a system fails or an anomaly occurs, Voyager must handle it on its own. By the time engineers on our planet understand there's a problem and send new commands to address it, 2 full days have passed. The situation could have shifted completely in that time. The New Horizons spacecraft, which flew past Pluto in July 2015, was roughly 4.5 light hours away from our planet during the flyby. All the information it collected during those few precious hours near Pluto had to be stored on board the spacecraft, then transmitted back to our planet over the following months. Every command sequence had to be programmed weeks or months ahead of time. Mission controllers couldn't react to what the spacecraft was observing in real time. They had to plan everything perfectly, anticipate every possible scenario, and trust that the spacecraft would carry out its mission on its own. Now, picture attempting to establish communication with a human settlement on a planet circling Proxima Centauri, 4.24 light-years away. You send a message asking how things are going, how the crops are growing, whether there are any problems that require addressing. That message moves at light speed for 4.24 years. 4 years, 2 months, and roughly 20 days later, your message arrives. If they respond immediately, writing their response and sending it right back, their answer requires another 4.24 years to arrive at you. That's over 8 years for a single exchange of details. You could ask about their latest harvest and receive an answer about crops that were eaten 4 years earlier. You could ask how a sick person is doing and receive news of their death years after it occurred. You could send advice or help, but by the time it arrives, the situation will have shifted completely. Any kind of real-time communication, the kind of immediate back-and-forth conversation we take for granted, is completely impossible across these distances. Conversations would be painfully, frustratingly slow. Debates would span decades. A diplomatic negotiation between our planet and a Proxima colony could require a century or more to resolve, with each party having to carefully consider their responses, understanding that years would pass before hearing back, and years more before their reply could be answered. This has deep consequences for governance and society that go far beyond just inconvenience. A colony 4 light-years away couldn't be governed from our planet in any meaningful sense. Any laws or directives sent from our planet would arrive years out of date. The political situation on our planet could shift completely between when a message was sent and when it arrived. By the time the colony receives orders from our planet, those orders might be obsolete, overturned by new governments or new policies. The colony would require to be autonomous, capable of making its own decisions on everything from resource allocation to conflict resolution to emergency response. Because waiting years for approval or guidance on every decision would be impossible. The colony and our planet would drift apart culturally over time, developing their own customs, their own ways of life, their own solutions to problems. They'd be linked by messages from the past, letters from another time, but unable to maintain the kind of immediate ongoing link that holds societies together. Over generations, they might turn so different that they'd barely recognize each other anymore. They'd share a common origin, a common history up to the point of separation. However, from that point forward, they diverge, developing separately, like species isolated on different islands. For more distant stars, it gets even worse. A settlement 10 light-years away would have a 20-year round-trip communication time. Messages you send to your children living there would arrive at them when they're adults, possibly with children of their own. Their responses would return when your grandchildren are grown, when you're old or possibly dead. You'd exchange letters across the decades like messages from different eras. You could share news and stay in touch in some abstract sense, but you couldn't have a relationship in any normal meaning of the word. A civilization 100 light-years away would have a 200-year communication pause. You could send a message and neither you nor your children, nor your grandchildren, nor even your great-grandchildren would live to observe the reply. Only your great-great-great-grandchildren living in a world you could barely picture might hear back from the distant civilization. The conversation would span generations, each generation sending messages to strangers they'd never meet. Folks separated not just by distance but by time, receiving messages from folks long dead. If you could move near light speed, something odd happens with time. This is Einstein's time dilation, and it's been confirmed by countless experiments. It's not speculation or theory in the sense of being unproven. It's observed fact as solidly established as gravity or electromagnetism. As you approach light speed, time slows down for you relative to stationary observers. The quicker you go, the more extreme this turns. This isn't just clocks running slow, this is time itself passing more slowly. Your heartbeat, your thoughts, your aging, your metabolism, everything happens more slowly from the viewpoint of someone who's not traveling with you. Though from your viewpoint, sitting in your spacecraft, everything appears normal. Time passes normally for you. It's everyone else's time that appears to be passing rapidly. Picture a spacecraft that could somehow reach 99.9% of light speed. Not quite light speed, but very near. You board this spacecraft and move to a star 10 light years away, then turn around and come back. From Earth's viewpoint, this trip requires roughly 20 years. 10.1 years to get there at 99.9% of light speed and another 10.1 years to come back. Anyone watching from our planet would observe your spacecraft require roughly 20 years for the round trip. However, because of time dilation, you would age much less. At 99.9% of light speed, time passes roughly 22 times slower for you than for folks on our planet. So, while 20 years passed on our planet, you would only experience and age roughly 11 months. You'd step off the spacecraft having aged under a year, while everyone you knew aged 20 years. Your younger sibling might now be older than you. Your children, if you had any, might now be adults older than you. You've moved into their future. If you moved even quicker at 99.99% of light speed, you could move to a star 100 light years away and back. From Earth's viewpoint, this trip requires over 200 years. However, from your viewpoint, due to extreme time dilation at this speed, the trip might require only a few years of your life. You'd experience a few years of travel time, living through a few years aboard the spacecraft. However, when you return to our planet, over 200 years would have passed. Everyone you knew would be long dead. The world would be completely different. Political systems would have shifted. Technologies would have advanced. Languages might have developed. You'd return to a future Earth that would be as foreign to you as if you'd moved forward in time. Let's zoom out even further. The observable universe is the region of space from which light has had time to arrive at us since the Big Bang. Space is roughly 13.8 billion years old. Light has been moving toward us for all that time. However, the observable universe is larger than 13.8 billion light years because space has been expanding while the light was moving toward us. The observable universe is roughly 46.5 billion light years in radius, making it roughly 93 billion light years across. This is the distance to the edge of what we can possibly observe. Beyond this distance, space has been expanding so quick that light from those regions hasn't arrived at us yet, and never will. There's a space horizon beyond which we cannot observe. Not because we don't have powerful enough telescopes, but because the light simply hasn't had time to arrive at us yet, given the age of space and the rate of expansion. Within this observable universe are an estimated 2 trillion galaxies. Each galaxy contains billions or trillions of stars. If you multiply it out, the total number of stars in the observable universe is estimated at around 200 billion trillion. That's a 2 followed by 23 zeros. And we understand from observations that most stars have at least one planet circling them. so there are probably similar numbers of planets, maybe even more. Space is filled with worlds, more worlds than we could ever count, more worlds than we could ever visit, even if we had unlimited time and unlimited technology. At the largest scales, space has structure. Galaxies aren't randomly scattered through space like grains of sand. They're organized into clusters, groups of galaxies held together by gravity. These clusters are organized into superclusters, massive structures containing multiple galaxy clusters. And the superclusters are arranged in filaments, enormous thread-like structures stretching hundreds of millions of light-years across space. Between these filaments are vast voids, regions with very few galaxies, empty spaces that can be hundreds of millions of light-years across. Space is expanding. Space itself is stretching, carrying galaxies with it, like raisins in rising bread dough. This isn't just galaxies traveling through space. Space itself is expanding, creating more space between distant objects. For nearby objects, this expansion is negligible, overwhelmed by other forces. The space between our planet and the Moon isn't expanding in any meaningful way. Gravity holds our planet and Moon together. The space within our solar system isn't expanding. Gravity holds the planets in their circles. The space within our galaxy isn't expanding. Gravity holds the stars together in the Milky Way. However, on larger scales between galaxies, and especially between galaxy clusters, separated by hundreds of millions or billions of light-years, the expansion turns significant and eventually dominant. Distant galaxies are moving away from us as space expands between us and them. The more distant a galaxy is, the quicker it's moving away. This isn't because the galaxies themselves are traveling through space at high speeds. They're sitting relatively still in their local regions of space. But the space between us and them is expanding, and the cumulative expansion over vast distances adds up to high speeds of moving away. For galaxies that are distant enough, space between us and them is expanding quicker than light can move through it. This doesn't violate the space speed limit because the galaxies themselves aren't traveling quicker than light through space. They're essentially stationary in their local space, but the space itself is expanding so rapidly that the distance between us grows quicker than light could cross it. It's like attempting to walk on a treadmill that's traveling backward quicker than you can walk forward. You're walking at your normal speed, but you're traveling backward relative to your starting point because the treadmill is traveling quicker than your walking speed. This means there are regions of space that are traveling away from us so quick that light from those regions will never arrive at us ever. Not in a billion years, not in a trillion years, not ever. There's a space horizon beyond which we cannot observe, not because the light hasn't had time to arrive at us yet, but because it never will arrive at us. The expansion of space is carrying those regions away quicker than light can close the gap. We are basically irreversibly cut off from those regions of space. Given the vast number of stars and planets, given that space is 13.8 billion years old, given that life arose on our planet relatively rapidly after conditions turned suitable, it appears likely that life should exist elsewhere, perhaps even intelligent technological life. And still, we've never detected any signs of alien civilizations. No radio signals carrying messages, or even just the electromagnetic noise of alien technology. No laser pulses, no megastructures, no signs of large-scale engineering projects, nothing. Space appears to be silent. This is called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The light year might be part of the answer. The distances separating stars are so enormous that they present enormous, perhaps impossible to overcome barriers to communication and travel. Our radio signals, our television broadcasts, Our radar installations have been leaking into space for roughly a century now. These signals move at light speed, spreading outward in an expanding sphere. They've now arrived at all stars within roughly 100 light-years of our planet. That sounds like a lot. 100 light-years is a huge distance by human measures. However, the Milky Way galaxy is 100,000 light-years across. Our signals have covered a sphere 100 light-years in radius in a galaxy 100,000 light-years across. That's a tiny fraction of the galaxy. We've barely announced our presence to our immediate space neighborhood. And even those signals are getting weaker as they spread out. The more distant they move, the more they disperse, spreading out over a larger and larger sphere. By the time our TV broadcasts arrive at a star a few dozen light-years away, they're so faint they'd be almost impossible to detect above the background noise of space. Even with very sensitive equipment, any alien civilization attempting to detect us would require extremely powerful radio telescopes pointed in our precise direction at the correct frequency at the correct time to pick up our signals. So what does all this mean for us? How should we consider light-years in our regular lives? For most folks, light-years don't affect regular life at all. You don't require to consider Proxima Centauri being 4.24 light-years away when you're deciding what to have for breakfast, whether to take an umbrella, or which route to take to work. However, there's value in occasionally stepping back and contemplating these scales. It provides viewpoint on our location in space. When you understand that our planet is a small planet circling an ordinary star, and that the nearest other star is over 4 light-years away, and that our galaxy contains hundreds of billions of stars, and that there are trillions of galaxies in the observable universe, it shifts how you observe things. Your problems, whatever they are, exist on a tiny planet in a vast universe. That argument with a friend, that stress at work, that anxiety about the future, that disappointment, that frustration, all of it occurs on one small world. The nearest star doesn't care about your problems. The galaxy doesn't notice. Space continues its slow development, completely indifferent to human affairs. This isn't meant to diminish your experiences or suggest your problems don't matter. Your life matters to you, and that's what's important. Pain is pain. Joy is joy. Love is love. These things are real and important regardless of the scale of space. However, sometimes when things feel overwhelming, when you're stressed or anxious or worried, it can help to remember the scale of space. It can help to remember that you're living on a small planet circling an ordinary star in a vast cosmos, and that from that space viewpoint, your problems are temporary, local, small. Not unimportant, but small, contained, manageable. There's also something beautiful about comprehending light years. When you look up at the night sky, you're not just observing points of light. You're observing stars that are light years away. You're observing photons that have been moving through space for years or centuries to arrive at your eyes. You're linked to those distant suns across vast distances of space and time. You're part of space made of atoms forged in stars, looking up at other stars, comprehending your location in the space order. Every star has a story. Some are young, just forming from collapsing clouds of gas and dust, beginning their lives as nuclear furnaces. Some are middle-aged, like our Sun, steadily burning hydrogen in their cores, stable and long-lived. Some are old, approaching the end of their lives, having exhausted their fuel, destined to turn white dwarfs, cooling slowly over trillions of years, or to blow up as supernovae, scattering their atoms across space to be recycled into new stars and planets. And all of them are separated by light years, by distances so enormous that even light requires years to cross them. Space is a sparse place with tiny islands of light separated by enormous oceans of darkness. And still those islands are linked. Linked by light, linked by gravity, linked by the fact that they're all made of the identical stuff, atoms forged in the hearts of earlier stars, scattered and recycled and reformed into new generations of stars and planets and potentially life. As our technology improves, our ability to measure distances in light years turns more precise. The Gaia spacecraft is creating the most precise three-dimensional map of our galaxy ever made. It's measuring positions and distances of over 1 billion stars. Future telescopes will allow us to observe even more distant. James Webb is already detecting galaxies over 13 billion light-years away. Future observatories might observe even more distant back, nearer to the Big Bang. We're also discovering more exoplanets every year. As of 2024, we've confirmed over 5,000 exoplanets with thousands more candidates. Many are dozens or hundreds of light years away. We're mapping what exists at these vast distances. In the future, we might send robotic probes to nearby stars. Breakthrough Starshot proposes sending tiny spacecraft to Proxima Centauri. Even if successful, probes would require over 4 years to send back information. However, barring revolutionary breakthroughs in how things work, light years will remain a basic barrier. The distances separating stars are vast, and light speed is limited. This isn't a problem to be solved. It's a basic property of space we live in. Comprehending light years shifts how we observe our location in space. And it raises deep questions about the future of humanity and our relationship with the cosmos. These aren't just abstract philosophical questions. They have real consequences for how we consider space exploration, the search for life, and the long-term future of our species. For most of human history, space was small. Ancient folks thought the stars were lights attached to a celestial sphere just beyond the moon and planets. The entire cosmos was contained within a space you could arrive at if you climbed high enough. Even when we understood the stars were distant suns, we had no sense of how distant they truly were. A few million kilometers, a few billion, the figures were beyond our ability to measure. So they remained abstract, undefined. It wasn't until the early 20th century that we began to accurately measure the distances to stars and understand just how vast space truly is. When Harlow Shapley calculated the size of the Milky Way in 1918, showing it was roughly 100,000 light-years across, many astronomers were shocked. Space was far larger than anyone had pictured. And when Edwin Hubble showed in 1929 that the spiral nebulae were actually distant galaxies millions of light-years away, space suddenly expanded again by orders of magnitude. We went from thinking the Milky Way was the entire universe to understanding it was just one galaxy among potentially billions. Today we understand the observable universe is 93 billion light-years across and contains roughly 2 trillion galaxies. That's a figure so massive it's almost meaningless. However, it represents a real physical space that exists all around us. Every direction you look, if you could observe far enough, you'd observe galaxies stretching away into the distance. More and more galaxies, until finally you'd arrive at the edge of the observable universe, where the light simply hasn't had time to arrive at us yet. This knowledge shifts our viewpoint in basic ways. We're not at the center of space. We're not special in any space sense. We live on a typical planet circling a typical star in a typical galaxy in a typical region of space. There's nothing unique about our location. If you were transported to another galaxy, billions of light-years away, you'd observe a similar view. Galaxies in every direction stretching away to the horizon. Space looks roughly identical from every vantage point. This is both humbling and empowering. Humbling because it shows how insignificant we are in space terms. The entire history of human civilization, everything we've ever done, every war fought, every empire built, every discovery made, all of it has occurred on one small planet, in one small corner of one typical galaxy. From a space viewpoint, we barely register. We're like bacteria living in a drop of water, completely unaware of the ocean that surrounds us. However, it's also empowering because it shows what we're capable of. We figured this out. We measured these distances. We comprehended our location in the cosmos. We constructed telescopes and spacecraft and mathematical models that allowed us to observe and measure things billions of light years away. We're tiny, but we're also amazingly capable. We're conscious beings who can comprehend space that created us. That's remarkable. Comprehending light years forces us to confront difficult truths about space exploration and the future of humanity beyond our planet. The distances involved are so enormous that they might represent basic barriers that no amount of technological advancement can overcome. Consider what it would require to send people to another star. Proxima Centauri sits 4.24 light-years away. With current technology, the quickest spacecraft we've constructed moves at roughly 192 kilometers each second at its peak. At that speed, it would require roughly 6,800 years to arrive at Proxima Centauri. That's longer than all of written human history. You could have launched your mission when people first invented writing, and it still wouldn't have arrived yet. To make interstellar travel practical, we'd require to go much quicker. Even at 10% of light speed, which would demand revolutionary new propulsion systems far beyond anything we can currently construct. It would still require over 42 years to arrive at Proxima Centauri. That's longer than most careers, longer than the typical span from graduation to retirement. And that's just to arrive at the nearest star. Most stars are much more distant. The engineering challenges are formidable. You require enormous amounts of energy to speed up a spacecraft to these speeds. You require to protect the crew from radiation during the trip. You require to provide life support for decades. You require to deal with the psychological effects of being confined in a small spacecraft for most of your life, never observing our planet again, moving through empty space toward a destination you might not arrive at in your lifetime. Multi-generational ships have been proposed, massive vessels that could support hundreds or thousands of folks for the centuries it would require to arrive at another star. The folks who arrive would be the distant descendants of those who launched. They'd have been born on the ship, lived their entire lives on the ship, and would finally arrive at a destination they'd only heard about in stories. The ship would effectively be a small moving civilization cut off from our planet, developing its own culture and society during the long voyage. However, even multi-generational ships might not be practical. How do you maintain a closed ecosystem for centuries? How do you prevent genetic problems from inbreeding in a small population? How do you ensure the descendants still want to complete the mission their ancestors started? What if they decide several generations in that they want to turn around and go home? What if there's a disaster, a system failure, a plague that wipes out most of the population? There's no rescue coming. They're light years from help. Some have proposed suspended animation or cryogenic freezing, putting the crew to sleep for the trip and waking them when they arrive. This would solve many problems. No requirement for decades of life support, no psychological issues from long confinement, no generational drift in mission objectives. However, we don't understand if such technology is even achievable. Can human bodies survive being frozen for decades or centuries and then revived? What about cellular damage from ice crystal formation? What about the effects on the brain and memory? These are all unsolved problems that might not have solutions. The reality is that interstellar travel with people aboard might simply be impractical given the constraints imposed by light's speed and the vast distances measured in light years. We might be confined to our own solar system for the foreseeable future, perhaps permanently. That doesn't mean we can't explore other star systems with robotic probes, but human exploration of other stars might remain forever in the realm of science fiction. The light year also shapes our thinking about the possibility of contact with alien civilizations. If intelligent life exists elsewhere in space, and many scientists think it probably does given the vast number of stars and planets, the distances measured in light years might make contact impossible, even if both civilizations survive for millions of years. Let's say there's an advanced technological civilization on a planet circling a star 50 light years away. They've developed radio technology and have been broadcasting signals into space for a century just like we have. Those signals are now passing through our region of space. However, they're amazingly faint after moving 50 light years, spreading out over an enormous sphere. To detect them, we'd require to be pointing very sensitive radio telescopes in precisely the correct direction, at precisely the correct frequency, at precisely the correct time. The chances of that occurring by accident are amazingly small. Even if we did detect their signals, consider what occurs next. We'd be receiving signals they broadcast 50 years earlier. If we responded immediately, our response would require another 50 years to arrive at them. That's a 100-year round trip for a single exchange. You could ask a question and die of old age before receiving an answer. Your grandchildren might hear the response to a question you asked. This basically shifts the nature of any potential contact. There can be no dialogue in any normal sense, no conversation, no negotiation in real time. Instead, it would be more like an exchange of encyclopedia entries. Each civilization sends everything they understand, everything about their history and science and culture, and hopes the other civilization receives it and responds similarly. It would be more like archaeology than communication, studying the records left by a distant civilization, records that are decades or centuries old by the time they arrive. And that assumes both civilizations survive long enough and remain interested in communication long enough for this exchange to occur. People have only been broadcasting radio signals for roughly a century. We don't understand if we'll still be broadcasting in another century, let alone several centuries. Civilizations might rise and fall on timescales shorter than the light travel time separating stars. We might detect signals from a civilization that went extinct centuries earlier, listening to the radio echoes of a dead world. There's also the disturbing possibility that space might be full of civilizations, but they're all so distant that none of them ever make contact. The average distance between intelligent civilizations might be thousands of light years. At such distances, even detecting each other turns nearly impossible, and communication turns pointless. Each civilization develops alone, makes its discoveries alone, asks its questions alone, and eventually dies alone, never understanding if anyone else was out there. Among the most deep consequences of comprehending light years is the realization of just how isolated we are. The distances separating stars are so enormous that meaningful contact or travel might simply be impossible, leaving civilizations forever isolated in their own small regions of space. Even within our own galaxy, even assuming there are millions of technological civilizations, the average distance between them might be thousands of light years. At such distances, communication turns almost pointless. By the time you receive a message and send a response, thousands of years have passed. The civilization that sent the original message might not even exist anymore. Their planet might have been destroyed by an asteroid impact. or they might have destroyed themselves in a war, or their star might have turned unstable and rendered their world uninhabitable. You'd be sending a message to ghosts. This creates a picture of space that might be full of life, perhaps even intelligent life, but where that life is forever isolated by the vast distances of space. Each civilization develops alone, asks its questions alone, makes its discoveries alone, and eventually dies alone, never understanding if anyone else was out there, never making contact with other minds under other suns. There's something melancholy about this. We've developed as social creatures. Link with others is basic to who we are as people. We construct communities, share knowledge, collaborate on projects. The idea of being alone in space, or of being surrounded by others but forever unable to arrive at them or communicate with them meaningfully, is deeply isolating. However, there's also something beautiful about it. It means every civilization that does arise is precious. If we're alone, or effectively alone, because we can't arrive at anyone else, then we carry a unique responsibility. Where space's way of understanding itself in this particular corner of space, the thoughts we think, the art we create, the science we discover, the love we feel, all of it is unique to us. We're not just one civilization among millions. We might be the only minds in our region of space, the only consciousness for dozens or hundreds of light years in any direction. This makes what we do matter more, not less. Every act of kindness, every discovery, every work of art, every moment of joy or link or comprehension, it all matters because it's occurring here and now and might not be occurring anywhere else nearby. We're alone, but we're also important. We're small, but we're also precious. We're insignificant in space terms, but we're also irreplaceable because there might not be anyone else like us for light years in any direction. Tonight we explored what a light year truly represents, how it's measured, why it's used, and what it reveals about space. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers, a unit necessary because everyday measurements become useless at cosmic scales. Even our closest stellar neighbor, Proxima Centauri, lies 4.24 light years away, a distance that would take thousands of years to reach with current technology. The Milky Way spans about 100,000 light years, and the observable universe stretches roughly 93 billion light years, containing an estimated 2 trillion galaxies. When we look at the night sky, we're seeing the past. Stars appear as they were years, centuries, or even millennia ago. Light years unite distance and time, revealing that space-time is deeply connected and governed by an unbreakable speed limit, the speed of light. These vast distances form real barriers to travel and communication. As the universe expands, accelerated by dark energy, distant galaxies will eventually disappear beyond our cosmic horizon. Yet despite this isolation, humanity has learned astonishing amounts about the universe, mapping stars, discovering exoplanets, and observing galaxies billions of light years away. Understanding light years is humbling. It shows how small and brief our lives are in a universe billions of years old. But it's also empowering. Despite our size, we've measured the cosmos, understood our place in it, and developed tools to study objects unimaginably distant. We are made of stardust, atoms forged in ancient stars, giving the universe a way to understand itself. When you look at the night sky, you're connected to distant suns by light that began its journey long before you were born. A light year isn't just a measurement. It's a reminder of our smallness, our uniqueness, and our responsibility. We may be isolated in space, but that makes life here more precious. It urges us to protect our planet, our knowledge, and our future. Light years represent both distance and connection, isolation and belonging. They remind us that while space is vast beyond comprehension, we are still part of it, able to understand it, and in doing so, understand ourselves.